All right, so we are not going to get through this presentation because the presentation is like
69, oh nice.
Yeah, 169 slides, yeah. So this is something we've worked on for a very long time. So this represents like a huge amount of work. So and it's very fleshed out. So and we've consulted with a lot of experts about this. We've had a lot of people give feedback about this. So we have tons to say about this. So my goal in this presentation is to just be like an introduction on what it is, kind of be like, this is what we're doing, this is why we need it. It is on the cutting edge of the industry. So we like that. We like working on the cutting edge of the industry. But before we do, so when we start talking about Coze here, let me get these out. Actually, I forgot to print these out. So we have handouts. It's just a one-page. Can you two share?
Yeah.
All right.
I'll share with the manual.
All right. Well, so before we do, I think we're going to talk a little bit about cryptography because Coze is like a cutting-edge tool for cryptography. So we have to talk about a little bit about cryptography before we can speak about Coze. So we know that Bitcoin's cryptographic, right? What does that mean? What does cryptographic mean? Right, so does Bitcoin do encryption? I've asked this question before. Does Bitcoin do encryption? No, right? Bitcoin does not do encryption, right? So what does that tell us? Cryptography is something larger. It's a superset than just encryption. There's more things. So I'm going to skip through this slide. So Bitcoin does two things though. Bitcoin does hashing and it does digital signatures. So Bitcoin signs things and Bitcoin also takes blocks and it takes a hash of the block and then you get a few bits out of that. So typically 256 bits is what we typically target. So the way I like to describe hashes, we'll very quickly talk about what a hash function is. A hash function is kind of like a shredder. You feed in paper into it, it splits it up, and then it puts it in a blender. It takes those shreds, puts it in a blender, blends it all up, and now your information's smeared over everything. So if you had written a piece of text, now your piece of text is now smeared across the entire thing. That's what a cryptographic digest does, is it smears your information across everything uniformly. So if anyone looks at your hash, it looks just like every other hash because everything's a gray goo blah, right? So that's the kind of start of it. So I'm just going to skip these slides because there's a lot of this. So I do want to talk about this real quick. Is cryptography is one of the most pure. Let me go Control 5. Is that how I do it? Thank you. Sorry, let me go full screen. Oh, that did not help. All right, well, I don't even know how to get out of that. All right.
If you hit dismiss or escape, that should probably work.
Okay.
But if you hit slideshow, it should start at the slide you're on.
Aha, Control F5, there we go, okay. So cryptography is one of the most pure applications of information theory. Information theory is something very fundamental. So we have some other things in here. I'm glad I included statistics, but there's all sorts of disciplines that are very pure applications of information theory. So AI is one of the new ones that's brand new, but it's purely based on information theory. Signal theory, so that would be like Wi-Fi, radio, some other things. This is kind of where information theory fell out of, was signaling theory. So Bell was trying to figure out how to communicate information. But we also have two others. In the green, they don't always like to be called part of information theory, but we like to include them. So mathematics is included in information theory through something called the Church-Turing thesis, and then physics is included in information theory through something called digital physics. This is the one, I think I've mentioned this before, that's the one with the 3 paragraphs on Wikipedia. So there's not a lot said about it, but it's interesting. But cryptography, because cryptography is a pure application of information theory, we share a lot of commonality with these other disciplines. So what these other disciplines do is very relevant for us. So one more slide. Well, so this is just saying, so we have cryptography, and then cryptography we can split up into smaller parts. So these are the areas of cryptography. So we have cryptographic hashing, digital signatures, key exchange, random number generation, zero knowledge proofs, homomorphic encryption, and encryption. Does anyone know what's the difference between encryption and homomorphic encryption?
Is it singular or?
So homomorphic encryption is where I want to do a process Like say I want to process over some data, like I want to, I don't know, like sort the columns in an Excel sheet, right? So I give that to Amazon, but I don't want Amazon to know what's in the Excel sheet. So I want to be able to encrypt the Excel sheet before I send it to Amazon. Well, how is Amazon going to sort columns if it's encrypted? Amazon can't read it, right? So homomorphic encryption is one of the cutting edge parts of cryptography right now, where you can encrypt your data and then still perform operations over that data. So that's why I have it in green, is that it's an area of intense research. It's very cutting edge. The other thing that is very, very hot in cryptography right now is zero knowledge proofs. And zero knowledge proofs is being able to do something without leaking any data whatsoever. And so has anyone heard of zero knowledge proofs?
Mm-hmm.
Okay, so
You told me during a run.
yeah, this is my favorite example of zero knowledge proofs. Is if I find did you guys ever do like Where's Waldo?
Yes.
Like the book Where's Waldo, and then you find Waldo on the page, and then you can share it with all your friends. So if I found Where's Waldo, how do I prove to Elliot that I know where Waldo is on the page, but Elliot can't know where Waldo is? So I don't want Elliot to know where Waldo is on the page, but I want to prove to Elliot that I know where Waldo is on the page. How can I do that? Right, so one way I can do that is I cut a piece of cardboard that's larger than any extreme of the book, cut a little hole for Waldo's face. I find Waldo while he's not looking, find Waldo, cover it up with the cardboard. Then I can show Elliot with the book covered. I could be like, look, here's Waldo, I found him. But now Elliot has no idea where Waldo is on the page. Zero knowledge proofs are crazy counterintuitive. They have to be one of the most counterintuitive things I've ever done. The proofs are usually very surprising, but that's the kind of tricks that they're doing, like covering up the book with a piece of paper, but you're doing it with numbers or bits or mathematics or something else. So Coze does these two things. Coze does digital signatures and cryptographic hashing. Coze does not do encryption. Coze doesn't do key exchange. It doesn't do all this other sort of stuff. Another really interesting one, this kind of seems weird, random number generation is part of cryptography. That just seems like a really weird one to have a part of cryptography. Why? Right? This turns out to be very fundamental to information theory. We probably don't have time to get into it, but securely generating random numbers is one of the most important things you do in cryptography.
Question. So something that we came across in our Java class was random numbers are not random numbers ever.
Yes, exactly.
So how is that different from the random numbers?
It's a whole area of study. So it's cryptographically secure or pseudo-random random numbers. So cryptographically secure random numbers is what we use. How that's implemented is Java. Like if you're programming in Java, Java is going to make a call to the operating system. And let's say you're running Linux. Linux then is listening to all sorts of things on your system, doing a hash over it continuously, and then producing random information. The assumption with it is that you have enough entropy on your computer that you can produce a random number that no one's going to be able to guess. So that's a big assumption.
Big enough list, long enough, yeah.
Yeah, so it's turtles all the way down on that one. But yes, most programming languages provide two forms of random. They provide a not cryptographically secure form of random, and then they provide a cryptographic version of random. The reason why you have the difference is typically the cryptographic version is way slower than the non-cryptographic version. So the non-cryptographic version, I can just produce tons and tons and tons. You will eventually run out, depending on what you're doing, with the cryptographically secure randoms. So, but yeah, PRNGs is what those are. So they're still pseudo-random. They're still not actually random. But.
And this is another question, but just let me know if you're going to answer this later. Why does Coze only do cryptographic hashing and digital signature only?
Well, so okay.
Or unless you're going to answer that later.
Well, then I think this is probably the right time to transition from this slide to go to the Coze slide. So I think that was Alt F5. Let's see if that works. Slideshow. Oh, it's Control F5. All right. So now we're in Coze. So Coze does digital signing. Why? So in science messages, so what's a message? It could be something that computer produces, it could be something, it could be a text, it could be something that you produce, it could be anything, right? A message could be anything. We have an example. So right now, things are kind of crazy in the world. There's all kinds of crazy things going on. But most people are on social media. Right? That's one of the things. We're creating a lot of messages. So one of those problems is we had one of the social media platforms, this little platform called Reddit. The CEO of Reddit didn't like what some people were saying for a while. So he decided to start changing people's messages. And there's no way to tell if you're changing someone's message. Like, so he can just go in the database, say, oh, they said this instead, upload it right to the database. Now Reddit says, oh, this person said this. But really, it was the CEO changing the messages in the database and then sending it to everyone. This is a big problem because, like, I use social media, but we have politicians and people in the military, and it's becoming a big deal. So we don't want these corporations to be able to change something that's very sensitive for politicians or whatever it is, or journalists. I mean, imagine how much journalism's done on social media now. I mean, it's basically taken over news. Journalism's almost purely on social media. So if a journalist is posting a video or a journalist is writing a message or something like that, it becomes very important that you can't change it. Well, and then think of it from terms of history. What if I want to rewrite history? What if in 10 years from now I want to say, oh, actually, you didn't report that. You didn't actually report that or say that, or I could fudge your numbers or change things or change your statistics in the future if it becomes convenient. And all it is I just change something in a database and poof, right? It's done. Yeah. Just change history, right? So this is becoming a really big issue. Another example of that, so that was like Spaz on Reddit, was changing people's comments. But another example is some of these, so everyone's probably heard of like the Wayback Machine. So that's a great web archival. They were recently hacked. I'm not sure if anyone heard what actually was the end result of that. But there's a lot of suspicion that that was actually a nation state hack, right? Because nation states have incentive to start changing history, right? If there's something inconvenience, there's some inconvenient truths, there's some inconvenient journalism on there, I may want that to go poof, right? So what do? I gotta change the website first, right? Or take it offline, but then I have to change the archive, right? I have to change the web archive. Right now, they are working, there's a cryptocurrency project that's working with them that will eventually start cryptographically signing. But a lot of these things are not cryptographically signed. That means we're just trusting the web archive, whatever they say is what history is. So now they have, right? It used to be that if you wanted to change history, you had to change the book on my bookshelf, right? Now, if you want to change history, I can just change a record in a database. So like that, this is just one application. Like this is one application I'm kind of passionate about. Like I care a lot about this, but there's so many other applications. Bitcoin does the same thing Coze does. So that would be another application of Coze is you can use it for cryptocurrency. You can use it for sending text messages, but anything that you need signature. So one more thing with the web archive stuff. We have the web archive. There's 2 other big websites right now. No one knows who's running them. And the costs are in the tens of millions, hundreds of millions to operate some of these websites. So why are some people running some of these archival websites and none of them are cryptographically secure? Again, is that a nation state actor doing that? Is that someone with good intent, or is that someone with nefarious intent, where they want to start changing articles or journalism or records so the future looks a little different than what we currently know it as, right? So there's a lot of power with this. But yeah, and it's concerning that we have these archival services that are just anonymous and no one even knows who they are. And they're not, and we whatever they provide, we're just trusting them right now. So Coze does a lot of that stuff. So, but as I said, it can be used for like, it could be used for like a social media system, it can be used for Bitcoin, it can be used for all sorts of stuff. So before I go into the presentation, any more questions? Okay.
I'll stop.
So there's probably like a lot of information. Yeah, and this is probably.
Get the question.
Well,
Wait.
I guess.
What were some of those websites you're talking about that people don't even know who's running them?
So archive.is.
Really?
Yeah, is
Okay.
like unknown. No one knows who runs it.
What?
And so
Crazy.
and we can calculate, like we know how much of the web it's archiving.
Mm-hmm.
Like we know how many hits it's receiving every day,
Yeah.
right? And they're doing stuff to get around paywalls. They're like orchestrated. They're doing a lot of work to
Yeah.
get that to work. No one knows who they are.
Wow.
I mean,
Wait, I mean, with that domain, isn't that domain out of Israel? IS?
so they've changed around a few
Oh,
times.
okay.
So I think they're at .is right now, but it was like archive.today They've hopped around a few times, and that's another really weird thing, right? Like, why is your archive hopping around? Like, and again, so if a nation state didn't like the original one, they could just ripped off the whole thing and started a new one and shut off the original, and we wouldn't have even known, right? There's no way for us to know, right? So like, we don't think about these like adversarial settings enough, but on the internet, everyone's an adversary. Right, in all the nations, all the people are on the internet. We need to be thinking about securing these systems so we can trust them in the future. So, any other questions before we?
Sorry.
Yeah.
I'll wait for you.
Well, if you are going to explain it later, it won't be an issue. But because he's doing two things: cryptographic messaging, or was it cryptographic? Yeah, messaging.
Yes.
And digital signature. What are those two?
Well, so hashing. So it does
Or
cryptographic hashing and cryptographic digital signing, or sometimes it's just called digital signing. So sometimes it's also just called DSA. So, but yeah, we'll get into that. I think.
Okay.
Maybe
Well, then if you're going to cover that, then that's okay.
Well, so hashing. So yeah, hashing is I can take an arbitrary amount of data. Say I can take a gigabyte, right? I can hash over that, and that outputs 256 bits, right, typically. So if I'm using SHA-256, so have you heard of SHA-256?
Yes.
Okay, so SHA-256 is like the gold standard right now, standard across the industry to use. There's also SHA-3, so SHA-256 is a part of SHA-2. There's also a newer family called SHA-3. It's not necessarily better, it's just different. So it's good. It's a good idea to have two different ones.
Yeah.
So SHA-3 also, you can do different settings on SHA-3, but SHA-3 also has a 256-bit output. You can, a lot of these, so SHA-2 also has a 384 output, also has a 512 output. So you can choose different sizes. And those different sizes are for your security. So that, we probably won't get into that today.
That's okay.
So, but how much your output of a hash is how secure it is. And so the big idea with the connecting the security of a hash to the security of a system is, that's like a big idea. But basically, however many bits you have, that's the security of your system. And like, how secure, what does that mean to be 256 bits secure, right? Like, what does that mean, right? Like, that's a weird thing to say. Like, we can measure security in bits, like, that's also a really weird thing to say, right? So, actually, the other presentation, maybe I should show this other presentation. This is like way down in the rabbit hole. Okay, yeah, so this would be an example of a hash output, right? So this is 256 bits. Right, so that's not that hard. I can write this out on a piece of paper pretty easily, right? Okay, and so like if I'm rolling a coin, right, rolling a coin, because we're talking in terms of dice, that's why we're rolling a coin instead of flipping a coin. But if you're flipping a coin, right, so you get 50% new information on every roll. So on every single bit, I'm 50% uncertain, right? That doesn't sound like that's really important, right? One question is like, so if I have this and this is truly random, and you start flipping a coin, how long are you going to have to flip that coin to get the same answer at 256 bits, right? So if you're sitting here and you're just flipping the coin, right, like, how long is it going to take for you to get the same answer, right? So you'll start, and then every time you're wrong, you have to start over, right? Like, how long is that going to take you, right? So this would be like an example of brute forcing it, right? If I want to just guess what your hash is, how long is it going to take? Okay. Oh, that's a really good. Okay, so let's not do any of this. Okay, here's the thought experiment. Okay, so here's a simpler way to put that. How about instead of flipping a coin, we just count from 0 all the way to 256, because that will include all combinations. Right, so if I count from 0 all the way to 2 to the power of 256, that's going to be every permutation of 1 and 0 I can do. Right, so we're just going to brute force it. We're going to do all of them. All right, so here's the question with this thought experiment. Have I done this thought experiment with you guys yet?
No.
Okay, this is my favorite thought experiment. This is like the foundation of cryptography. The question is, how much energy is it going to take to count to this number? That's a weird thing to say too. What do you mean how much energy? Like on my laptop? Right? Like, do you mean in a data center? Do you mean like with an old computer, like, what do you mean, like, count to this number? And so we're going to be even, oh, so if I convert that number, by the way, so that's in binary. If I convert that number into decimal, that's what that number is. So it's still, I mean, it's big. It's not that big, right? Still, I can show you on the screen, right? So what we're going to do is we're going to go ask the physicist, and we're going to ask the physicist, how much energy does it take to flip a single bit if you were to use the absolute minimum amount of energy that it takes to flip a single bit, right? And the physicists have an answer, and it's called the Landauer limit. So the Landauer limit is how much energy it takes to go from a 0 to 1, right? So, and then we're going to start using various sources of energy around Earth to try to count to this number, right? So we're going to start with one solar panel, and with one solar panel in 1 year, according to the physicists, we can count to this number, right? So that's 33 of the 78 digits, right? Okay, that seems like we're making pretty good progress with just one panel, right? But we want to do all 78 digits, right? This base 10 number. So this is old. This is way old. But Bitcoin used to be the 40th largest electricity consuming country, right? It's like much higher now than when this came out. But if we were to use all the energy that Bitcoin uses in its mining, we can get to 40 digits. So from one solar panel to all the energy that Bitcoin's using, we only went up 3 decimal places. That's not very good. So you could probably guess what the problem is now, right? We're going to use all the nuclear power plants, right? We get to 41 digits. That's no good. All right, so we're just going to go extreme, right? We're going to be like, okay, sci-fi. We're going to go sci-fi now, right? So we're going to do a Dyson sphere. No, that doesn't work. Why don't we just take Earth, put it in a blender, E equals MC squared, and see how many digits we can count, right? So if we take the total mass energy of the sun, right, we can get to 70 digits, just counting to 2 to the power of 256, right? We're still 8 digits off, right? So we have to consume 100,000, right? Yeah, no, 100 million. 100 million suns to be able to count to that digit. That's what it means. So like cryptography is trying to preclude computers that can break these things, right? So the big idea with this is you can count until the sun dies, there's no star left in the sky, the whole universe is cold and dead, and you're still not going to get to that number, right? You're going to have to start consuming galaxies of matter to start counting to these numbers, right? So there's not going to be a better computer that comes out that can do this. So that doesn't answer your question.
No, but it's great information, so I don't want to say no.
So yeah, but this is starting to get there. So like if we talk about Moore's law, right? Like what's the fundamental limit of Moore's law? Well, it's the Landauer limit, right? And how far away are we from the Landauer limit? I think we're like 78 digits still or something crazy like that away from the Landauer limit, right? Like computers still phenomenally inefficient according to physics, right? So we'll get closer. But even when we're at the bare minimum, when Moore's law is done and finished, we still cannot break these codes, right? So that's what cryptographic hashing and cryptographic signing is trying to get this property built into it. Trying to get this property that even if you have all the computers in the galaxy, you're not going to be able to break these things, right? Because it's going to take too much energy and too much mass energy to be able to break it. Okay, so any more questions before we go?
No, I didn't know that. That is so cool.
Yeah,
I did
that's
not know that.
so. In the history on that, Newman, John von Neumann, yeah, von Neumann architecture, yeah. So, are you familiar with John von Neumann?
I'm not sure about that. You said the architecture, like.
Well, yeah. So, the computer architecture that we have is called the von Neumann architecture. So, with like a processor, RAM, and stuff. If you're in mathematics, computer science, or physics, you run into von Neumann.
Okay.
He does all sorts of stuff. But von Neumann's the first one that came up with this. He said, okay, like we have the second law, and in the assumptions we have the second law of thermodynamics. If computing has to consume so much energy, otherwise the second law of thermodynamics, which says entropy should always increase, actually decreases. Right? So there's a minimum amount of energy you have to consume for entropy to always increase. And that's what, it was actually first the von Neumann limit. Landauer, I'm not sure if I agree with Landauer, but it's currently like accepted that it's probably the best answer we have right now. And this is all theoretical. None of this has been actually tested experimentally in a lab. There's a lot of discussion about doing it. But Landauer said, well, actually, it's operations that are irreversible. You have to count. So there's a distinction, but Landauer is the one that gets the name for it. So if you're at the bottom of this stuff, very fundamental work, Landauer is the one that you're going to run into. Okay, so
Sorry.
Yeah.
So all the energy talk is as if we're in a perfect vacuum. We're not losing any of it in any of the sort, and that it's going to be instant, essentially.
Yes.
Instant, like. All right.
yeah, there's no waste. You're doing perfect calculation, right? And all we're doing is counting. We're doing no other operation. So we're not doing comparisons. We're not doing anything else. You wouldn't even know you were done. That's the other problem with it. Because we didn't compare your result with anything else. We're just counting, right? So you might just flip over and keep on going, and we wouldn't know when to stop.
Yeah.
Right. So, all right. Okay, how much time do we have? Okay, kind of. All right, I think probably we'll do the first part of this. So Coze in 2 minutes. So we're going to go to theory 2, practicality. Now, so maybe it's a little bit background on this. Cipher.me, we're doing cryptographic codes. So this would be like an example of cryptographic code in a QR code. So if you scan this, it has 256 bits of entropy. It verifies something on the website. You can look it up on the website and it verifies whatever it is. So right now I just have this code. It just brings up this water bottle. It says it's Zach's water bottle, which is pretty cool. The idea is with that product line is there's a lot of counterfeits on Amazon. So Amazon hasn't been doing a good job cracking down on counterfeits. So if you buy vitamins from Amazon, you don't know if you're actually getting from the manufacturer or if someone else shipped it to Amazon. Amazon's point is, hey, it has a UPC code. We don't know who this is. We're just scanning UPCs. So we started developing Cipher.me to solve the problem of counterfeits. That was the practical application. Amazon tried to hire us to work on their solution, and it's called transparency. So if you buy something from Amazon and you see a little transparency code on it, they don't use QR code, they use data matrix, I believe. That's a ripoff of us. We were working on that, and Amazon literally tried to buy us, literally tried to do our stuff, and we were not with those terms, and implemented their own. So that's kind of a fork in my career. That's one of the things that could be we could go with them. But we needed something to sign these. We needed something to sign the QR codes, right? So we were waiting for the industry. The industry really hasn't come up with anything yet. So let me actually go to this slide. There's a problem in the industry is that we have primitives. So we're just talking about signing. We're not talking about anything else in cryptography. There's a whole bunch of things that you can choose from, right? So there's ES224, there's ES256, there's ES384, there's ES512, ES256K, ED25519, ED25519PH, and then there's a whole bunch of other ones, right? There's new ones coming out. There's post-quantum algorithms coming out. The problem the industry had is that no one standardized these things. So if I wanted to write a system to sign something, I have to pick one of those algorithms, let's just say ES224, build it into my system, and then that's all my system can ever talk on is ES224. Is that a good idea? Probably not, right? Because what happens if ES224 has a break, or someone finds something wrong with it, or what if it's not considered secure enough for the application, or there's lots of other things that can happen. So the industry really hasn't come up with a solution to this problem yet. So we were waiting, this was about 2017-ish, we were waiting for the industry to come up with something. Microsoft released something called JWT, which is JSON Web Tokens, came out with it. We tried to implement it and it was not what we needed, right? So at that point, we decided to create Coze. So one of the things that Coze does, so I'll go back to the slides that we skipped over. Coze takes these primitives, it puts it in a common abstraction, and then your application can use signing. So if you're saying, hey, my application needs to be able to sign messages, like I'm doing whatever, I'm sending text messages, I'm sending social media messages or something, you say, that's my application, I need to use one of those primitives. You can use one of those primitives, or you could just use Coze. And Coze is standardizing it and it's making it easier to use. And we'll get into the kind of the pieces of that. Okay, so let me go back over these slides. This is an example Coze. So it's a JSON message. So, and everyone's familiar with JSON. So JSON is a way to communicate your data, right? So it's like, okay, I'm going to send you data. Well, how do I structure that data? Right? Computers don't like just blah, right? You got to structure it in some way. So JSON is a way to structure data, and it's the most popular way to structure data. So another way, like I'm old compared to y'all. Right? So before JSON came out, XML was being used. So you know HTTP or HTML. I don't know why I'm stumbling over this. HTML is kind of based on XML. So you have the open bracket, you write something, end bracket, you put your data, and then end bracket. Programmers were like, that's way too much, right? Like to structure our data in XML is way too much. So JSON came out in, I want to say it was the mid-90s, and when JSON came out, it took over the industry. So essentially, if you're going to send data between systems, so if you're talking like API calls, so if you're going to a website and your computer needs to be reading messages from that website. So say, I need to read all the messages from this user, right? So I go to this API, which is just a web address. That web address is going to dump something that looks like this, right? And this is what APIs typically do. Well, APIs nowadays are almost entirely JSON. So the key thing with JSON is you start with the opening brace, and then you have an ending brace. So that's JSON. So Coze, when we came around, we were like, okay, everyone's using JSON. All systems already use JSON. Like, why don't we just do cryptography on top of that? Because that's what we need to sign. So JWT, the spec that Microsoft released, they tried to do that. We don't have time to really get into it, but we did not find the way they did it to work really well. Let me give an example, actually. Way down here. Okay, yeah. So, like, this up here is an example of a JWT, right? So it's just dark gook. It's not human readable, you can't see it. So when Microsoft released that, we said, hey, that's not even JSON. What are you guys doing, right? Like, why are you sending gook? I can't read that. I don't know what's in that, and why are we sending gook? There's no need to do it. There's other problems with it. We won't get into it now. But we saw that and said, hey, like, why don't we just make it human readable? Because that's the whole point of JSON, is JSON's human readable. So we actually know what the data structure is and sign that. So that was the start of Coze. So then in Coze, so I think we could probably, so we'll come back to that. Let's talk about the rest of it. Coze is a cryptographic JSON messaging specification, right? So Coze uses digital signatures and cryptographic hashes to ensure secure, human readable, and interoperable communication. Coze is a cryptographic abstraction layer. So sometimes I've even been calling it like a language to speak cryptography, digital sign. All right, Coze is open source. It's 3 clause BSC, so it's fully open source. So speaking of which, we would love any contributions, and we have tons of things to work on with Coze. So if you're ever bored and want to help us with this, I mean, we need help with editing, we need help with documentation, we need code help, we need other refinements. So it's open source. You can do a pull request. We will see them. We do get pull requests. People send us stuff all the time. But that's one of the nice things about this. Okay, where did Coze come from? The word Coze means in English, it's actually Coze is how you're supposed to pronounce it in English. It means a friendly chat. And so when we looked it up in the dictionary, we said, hey, that's the perfect name for a messaging standard. A friendly chat, that's great. All right, so when we already went over this, is cryptography has all these primitives and there's more coming. Like that's the other thing, is the industry had a whole bunch coming and they all work very differently. Some of them have very small signatures, some of them have gargantuan signatures. Some of them have references, some of them don't. Some of them structure the keys differently. All kinds of wacky things that you wouldn't expect. Coze takes care of that. You don't have to worry about any of those details. So these are our design goals. Has anyone heard of the word idiomatic? It's a programming term. So it's a technical term. So idiomatic means to do something in the way it's supposed to be used, right? So it's like you could get a screw from Home Depot and you're trying to connect 2 pieces of wood together, and you could get a rock and you could smash the screw into the 2 pieces together, and then that would work, right? Like you could use the screw that way. But that's not how screws are supposed to be designed for. You're supposed to get a screwdriver, screw in the screw, and then that works a lot better, right? So using a rock to smash it in. So the idiomatic use of the screw is to use a screwdriver. You see it all the time in engineering. People use rocks all the time in engineering, right? So one of the things we're saying is we're trying to use JSON the way it's supposed to be designed, which means chiefly it's human readable. Another design goal is small in scope. I know I said that like I could talk a lot about this, but the goal is the spec is really small and our rationale is really large, right? So the end output of the project is a tiny library that is very easy to understand, but we have a ton of rationale for why we're making very specific decisions, right? And then provide defined cipher suites. This is like kind of hard to define, but Coze tells you how to use each primitive. Coze provides guidelines on how to use a particular primitive. And some of that kind of exists in the industry right now, some of it doesn't. I think the way Coze does it is very agnostic. It's a great way to do it. So, okay, so now let's actually go over how this is done. Okay, so like we want to build this. So say we want to build a Coze payload. How do we do that, right? So this is the steps on how to sign a Coze. First, you have data of some sort, and we're going to put your data into JSON. Then we're going to add your Coze fields. Then we're going to remove unneeded space, and that's, well, I forgot what that's called. It's escaping me right now, but, minification, that's what that's called. So you minify your text, so you don't have any extras. You minify it down to the absolute necessary, and that's what we're doing with the remove unneeded spaces. Then we hash it, and then we sign it. So let's do it. So let's go through that. So here's an example message. Here's your data, Coze rocks, right? This is your data, you want to sign it. We JSONify it, so that was easy, right? We just put braces around that. That was really easy. This is why programmers love JSON, right? It was that easy. All right, so then we have to add the Coze fields, right? And so Coze has your payload, that's what pay is for. And then we have the Coze fields. So alg tells us which primitive is being used. Then we have IIT, which is your timestamp. It's your Unix timestamp of when this message was signed. Your thumbprint, which is the key that is used to sign that message. And then an optional type, which is just telling me what sort of data is this, right? So your system can say, oh, hey, this is just a message. So in this particular instance, we said this is a cipher.me/message. So that tells your computer what kind of message it is. And then we append a signature at the end, right? So sig is for your signature, and that's your cryptographic signature. All right, so that was a little fast, right? I love this meme, by the way. I don't know if you've seen this meme, but let's do it again, right? So any questions before we do it one more time? Okay, so you put your data into JSON, right? We're good on that. You add your Coze fields, right? So alg, IT, thumb, and type, and they're all optional, by the way. Every single one of those fields is optional, but it is best practice to use those 4 fields. We remove spaces. Okay, so this is the minification. We didn't show that before. But this is how we remove spaces. This is JSON minified. So JSON doesn't need spaces. So we don't want to sign over spaces because any change in your JSON completely changes your signature. So we want something that's deterministic. So this way it's standardized. We hash it. So the hash of this input is this. So we take that hash and then we sign the hash, and this is the output signature of the hash. And then we put it all back together. We say, there's our signed Coze message. Right. Easy enough, right? All right, so you might notice, you might not notice. What is signed? Well, everything from brace to brace is signed. So your payload is everything brace to brace, and then we serialize it and we sign it. Anything that's not in your payload is not signed. So I can put other fields outside of my signature, like foobar, right? If you know foobar. Yeah. All over programming, you'll see that. Bob and Alice and foo and bar, you'll see that all over, right? But foo bar is not signed, and the signature itself is not signed, and the word pay is not signed. It's just what's inside the payload is signed. All right, so also kind of wondering, okay, so how do I use Coze in my application, right? So you have fields. Your application is going to have some fields, and almost certainly it's going to be in JSON. You need to add Coze, so we're going to encapsulate your data with Coze. So it's your data, we're just going to wrap it like an onion, right? Then we're going to transport it, Then on the other side, whoever's receiving your data unwraps that onion, verifies the Coze, and then you get your fields back out. So at the end of the process, hopefully you don't see any difference. The only thing Coze's providing is an authentication layer. So everyone can be sure that the data was signed. All right, so I think we're probably going to end there. I think that's good for today, right? Does everyone feel like that was a good starter? So,
Do we want to try it or no?
well, yeah, we're going to try it.
Yeah,
Okay,
let's try
okay.
it, let's try it.
But everyone feeling good?
Yes,
I know
it
this
is
is
really
like,
cool.
Good enough.
okay.
Yeah.
Yeah, it's a lot of information. Okay, so this is,
No, it's a lot of information. I'm listening, yeah.
So this is what the website looks like?
yeah,
Oh, this is cool, okay.
yeah, so,
This is really cool.
by the way, yeah, so has anyone seen like Touchstone pictures, like the movie producing Touchstones? Okay, so we
The
modeled,
little lightning bolt.
yeah, so we modeled our logo off of a touchstone. What's a touchstone?
I don't even know.
Yeah, great question, right?
Yeah.
What is a touchstone? Okay, so back in the day, you had some gold coins, but people also had fake gold coins.
Mhm.
So how did I tell the difference between real gold coins and fake gold coins? I used a touchstone, right? So I would take your gold coin, I would rub it against the touchstone,
Yeah.
right? I would look at the glitter on the touchstone and be like, oh yeah, that glitter looks like gold, right? Well, as in if your stone was fake, it wouldn't have the same shimmer on it. So the touchstone was a tool used to verify that gold was authentic, right? So the same thing, that's what we're doing. These messages are touchstones being used to verify these messages are authentic. Okay, so very quickly, what do we want to say? Hi, Elliot?
Yeah.
Sure. Hi, Elliot. Okay, so we're going to sign it in there. That's it. So we have the output, right? You can see all this, right? So that's our output. Do I need to zoom in? Can you all see that?
Where would you put this output in, kind of?
Okay, so then we're going to
Yeah.
verify it, yeah. So let's delete the message, put in here. All right, so this would be an example of putting it, this just transported, you just
Okay.
moved it someplace else. Right, so I could have texted you this message, and I just hit verify, and it verified using my key. Right, so I also have to send my key using this website, so it's down here. This is the Coze key that was used to sign the message. So I have to send you the key and the message, but as long as you have the key and the message, you can verify it. So one of the problems we found with like Microsoft's solution is they did not implement their solution. They just made a spec, and they didn't actually like see if it worked or see if it worked when you wrote it in code, and there was a ton of problems with it. And so they've had to release all kinds of updates to kind of fix the standard. So this is one of the reasons why we did this, not necessarily because, well, it is useful. You can use this tool for this sort of stuff, but this helped us create the spec in the first place. It's because if we can get to here, and we had to implement this in code, so this is running in JavaScript, this is running in the browser, no part of this is running on the server, all of this is running on the browser. We had to make sure that JavaScript was compatible with what we were thinking of doing. So we've implemented Coze in 2 languages, JavaScript and Go. We have someone implementing it in Rust right now, and we've had some people try to implement in Python, but we haven't endorsed any of the Python forks of it just yet. So I don't know enough Python to be confident in it. I know enough Go that I'm pretty confident, and JavaScript we can get along with JavaScript to make sure it works well enough. But yeah, so that's it. So, all right, that's the end of the presentation. Any more questions?
So how do we deliver the key? Without like accidentally sharing the key to everybody, to our message? How do we deliver that safely?
So it is a public key.
Oh, it is a public.
Okay.
Yeah, so you can just copy and paste this. I can send this, like I can print it out and give it to you,
Okay.
right? Or, I mean, what else can we do? I can send over text message. Cipher.me, so this is part of what we're doing. Like you can see, I'm actually signed in, right? So part of this, I'll show you this. This is kind of cool, right? I have keys that are on the system. So this is my public key that the system knows. And so the system's tracking my account. So it's tracking this. You could scan the QR code, but the system just knows that's me. So I could, actually, was that using my mobile key? Oh yeah, it was using that key actually. Yeah, so if you pull up this, if we do a private window. Okay, so because it's a private window, I'm not logged in. You have to actually create a new key first. So this just created a random new key, and I can sign anything. So we're going to say hi Josh this time, right? So, but then I have to send, I'll have to send that other key, which, where is it? I don't know. Oh, is it not showing it? Okay, well, that might be a bug. Should be showing that key. Well, it's right here. Did I miss that before? Did I just
It was
scroll over
up there,
it?
yeah.
Oh, okay, well darn. It was there. I'm like, it's that bug. But anyways, yeah. So I would send that key along with any message that you send. So this tool, you can import your key as well. So we don't want to be creating a new key every time. But yeah, so that's it. So, oh, yeah, one more thing. Because this is kind of a complicated tool, people with cryptography are very suspicious, rightfully so.
Yeah.
We have a way simpler version of that without the bells and whistles. And so this is a simple verifier, and there's no magic that happens on this page. In a single page, a little bit of JavaScript, and it's all in one file. So if you're in a high security setting and you need to be able to verify a Coze message, I can load this onto a secure laptop somewhere, and I can use this page on the secure laptop to actually verify the messages. So this would be an example of someone that's more paranoid. Like, I don't trust being connected to the internet. You can load this page, not be connected on the internet, and use your browser on a web or air-gapped machine to do this. So, any more questions?
That is so cool, this one. I don't know. It makes sense if you don't want to be on the Wi-Fi to like do all this, but
Yeah.
that's cool that you have this option. Because did Microsoft have this option when they
No.
were trying to see?
They still don't have this.
See?
Like, and we're talking about years and years later.
Oh my gosh.
So, yeah, as far as I know, this is the only one that does this. So,
That is so cool.
and it's this tool itself is fully open source. So
Oh,
this
so cool.
this is the code for that tool. Anyways, I have another actually example for this.
Yeah?
This is really, we ran into another problem. Let's see if Google will say yes. Oh, not robot Google. Oh, goodness gracious. I think I'm doing this wrong because I'm including the dude. We'll see.
It's so funny. The dude is a bike, guys. No. Yeah.
Apparently, I look like a machine because it's not happy yet.
What the heck?
Okay.
Oh, dang.
Yeah, Google thinks I'm
You're a little answering
a robot. Okay. Yeah. So we're the number one tool on this. So when you
What?
one of the primitives is ed25519. When we were trying to find tools to work on Coze to implement it, the first result on Google was some anonymous person that would take the private keys and send it off to a server. So like this stuff, like, and people were putting their keys in there. So we had to make this tool. So now this is the number one tool. The other tool got taken off of Google. But this is a great example between the two, right? Like this is an example of a single primitive and all the options you need for a single primitive. Coze says, okay, well, that's too many options, right? Like just do this, right? Because you need to do all these options for every primitive that you have. You have to
Okay,
specify.
so the other one's like a simpler kind of version of this.
Yes, this is a
Okay.
single primitive.
Single, okay, this
Yeah.
is only for the ED25.
519, yeah.
But then you can, with the algorithm one, you could change it though, but you would have to know which one you're like.
Yeah, so
Okay.
yeah, so Coze, we can do any of these algorithms, right? So we
Okay.
could do like 512 and we can sign it, right? And there we go. There's a signature using 512. So yeah, or sign it using 256, right? And all that's changing is the signature size on that. So if we
And
go to 512.
When it says generate a random key, is that like a public one?
Oh no, I got to generate that. That's actually, there we go. That's actually 512.
Okay, okay.
So that should be clearer on that tool to make sure that that's it. But, oh, sorry, what was the?
So that you were saying that when you generate a random key, is that like also just public, all of them public and everything?
Yeah,
Like
so
that?
this is actually the private key. So
The private key, okay.
we didn't cover this in the presentation, but Coze specifies Coze keys. So we
Okay.
specify a way to serialize keys. And what Coze says is there's two parts to a key. There's the public part and there's the private part. The public part has to be serialized into X. So if you see X is your public part of your
Okay,
key, and then D is your private part.
okay.
So as long as you delete D in a key, you're good to go, right? Before I
Okay.
send it off to somebody, I can just delete D and we're solid. So, and D is like a crypto standard, like everyone always labels the private key D. That's why it's the private key.
Oh, I didn't know that actually.
Yeah,
That-
well, that's probably the worst part about it is like, what else would you call it? We could have like called it private key and like made
Yeah.
a big old, but
Yeah.
we figured this is good enough.
Okay. Yeah, just shorthand everything, make it simpler, I guess.
Yep. So,
Okay, that's cool though.
but yeah,
But
so,
they do the same thing, right?
yes.
Okay.
Yeah, so this would be an example of using Ed, and yeah, we're number one on Google, so I'm happy
That
about
is
that.
really
So-
cool. I was like, wow.
So we have a few things like that. I'm always forgetting.
Number one in Google, that's a good thing.
Yeah. So Coze is number 2 on Google now.
Wait, who's one?
What's their name? ByteDance.
Do you know them at all?
Really?
Yeah.
You do know them.
Well, no, I mean they're like the biggest company in China. It's ByteDance.
Oh, okay. I didn't know that.
They were TikTok before,
Yeah.
I guess,
Yep.
before it was sold, I guess. I don't really know what happened with that, but yeah, they were a company that
Yeah.
owned TikTok.
Yeah. So and ByteDance. Oh, so we looked up the name Coze. No one had it, so we started using Coze. But then ByteDance called their AI Coze.
Are you serious?
Yes, so we're going to have to,
I'll wait for
this is future, we're probably going to change the name Coze from C-O-Z-E to C-O-Z. Because then that way we avoid conflict with ByteDance.
Wait, what?
Yeah.
That's so crazy they did that.
Yeah, but I mean, like, they were like, hey, let's just
Well
call it
then,
Coze.
why
So.
is like everyone wanting so hooked on the Cozy?
Because we're cool, we're
I know.
trendsetters.
Well,
What
that's
if they
true,
dropped
but
the E
like,
on
why?
theirs? Would you?
Could you add an E as well? Just cozy, so it'd actually be cozy?
Yeah, we could.
Yeah.
But we do want to, we want it to be Googleable. Like if I'm looking up documentation, so what's something that I can Google, and COZ seems to be pretty, no one's
Less
using that.
characters is better.
Yeah. So yeah, I'll show you. So if you Google Coze
Or
JSON.
CO2.
Oh, come on, Google. Well, maybe we lost internet. Nope. So yeah, see, we're number 2 now. So ByteDance is number 1. We're number 2.
That's crazy. What?
Yeah. So we used to be number
Do
1.
they do the same thing?
No. So this is their API for their AI.
Why did they name it that then though?
Because they could. Yeah. So.
Similar
Oh my
thought
gosh.
process, I'm sure, too.
Yeah. So we have a few things we're going to change with Coze. We are
Why
kind of.
can't they change it?
I know. Well, it's kind of hard to go to ByteDance and be like, hey, change your name.
We need you to change this by Thursday, guys. Okay, if not, you're gonna be in some trouble.
Yeah. So
Okay. When did they do that? When did they
I want to say it was about 2 years ago.
Oh dang. Dang, you've been working on this for a while, guys.
Yeah. So if we go to okay, so this is Coze.js. No, I guess we can just click on this one.
You did say you started in 2017, right?
I want to say it was close to that.
Or at least the dream started in 2017.
Yeah, so like you can kind of see like nothing's really been touched in 2 years. I just updated the README right before we got here, but we haven't done anything to this in 2 years.
Okay.
So, but there's all kinds of things.
But
we can do.
it's probably so you're saying it's mainly like it was finished 2 years ago. At
Yeah,
least. Everything was fleshed out and everything.
Yeah, we feel pretty solid with it.
Okay.
Well, and it is used in production. We don't even know all the businesses that are using it.
I just was gonna say, do you have people just like do you know a business at least that is using this? Probably a lot, like even little ones that you might not even know.
Well, there's a few. Like we have some friends that are using it too.
Yeah.
So.
Okay, cool. And they have like their own businesses and
Well,
stuff.
they work for people. So I don't know. I should ask more. I don't
Yeah,
even
no.
know. Yeah.
I mean, it's just nice you built something for people. What you should know who's like all using it. That'd be
Well,
awesome.
just for feedback at least.
Yeah,
too.
for feedback.
Well, so, we've gotten one of the people that reviewed this is Loop Valiant, and I'm not saying he endorses the project. I don't want to put words in his mouth,
Okay.
but he did review it,
Uh-huh.
and that's the 4th largest crypto library. And he runs Monocipher. That's called Monocipher. So we've had like feedback from some pretty solid people. Another one is Kyle Isom, who was essential in Let's Encrypt. And for Cloudflare, he wrote all kinds of stuff for Cloudflare and HTTPS. He wrote a large part of the Go libraries. I'm pretty good friends with the person that wrote the Go client for Bitcoin.
What?
They've looked at it.
That's so cool.
So we have people that have looked at it. I do get messages from, I had one in particular. I had someone write me and said, hey, we're deploying this on 100,000 servers. We just want to make sure you're a real person.
You're
I was like,
lying.
No, so like, but they wouldn't
That's
tell
so
me anything
cool.
else, right? They're like, for
Wow.
security, we're not telling you anything else, but we just want to verify you're an actual person.
Yeah, they're like,
Yeah.
this is real, right?
Yeah.
Some AI generated video of you saying, yeah.
Yeah.
I would be like, oh, we gotta not do this.
Well, so in JRIG,
Two at the bottom.
Yeah.
JRIG doesn't like this because he doesn't like JSON. He's like, you shouldn't do JSON. He's not a fan of it. But Jason wrote, JRIG, he wrote the Bitcoin primitive is called ES256K. The K is the important part of that. He wrote that, and he's looked at this. So like we have people that looked at it, and I'm not saying JRIG definitely does not endorse this.
So you guys had like gotten feedback from those people too? Then?
Yeah, I think we've had some really good feedback.
And because of that, you guys are able to like kind of. Was there anyone who was like, oh, I wish you guys could add this, or like, was there any people who didn't like it, and you just had to fix it and it was perfect?
The biggest complaint we've had is JSON.
Oh, okay.
People are saying you shouldn't be doing this in JSON, and I feel like I don't feel like that's a reasonable answer. So the other alternative is we could have done this in binary, and I think that's totally reasonable. Like doing this in binary is very reasonable, but if you want a human readable format, what are you going to use? And there's no response to that question.
Do you think maybe later in the future you guys could since you said this is like open source, right?
Yes.
Could someone make a way to have it also binary instead of just like?
Yeah. Oh, actually, we have a starter spec for that.
Okay,
yeah.
That is so cool.
So if someone wanted to do it, and they could start all over, but we put out our initial thoughts on how you implement this in binary.
Cool.
There's another unfortunate name conflict with Coze. There's another standard called COSE, and they do binary encryption or not encryption signing. This Cozy thing. I know. It was and I wish we would have thought about that. But they're using instead of using JSON, they're using CBORD, which is just a binary format. But yeah, the biggest complaint we've had is people don't like JSON. I understand why people are afraid of JSON. There's lots of hard, sharp edges with it. But reading our document, I think we nail every single one of those concerns. We didn't get to it in the presentation, but the way that Coze addresses that, do I have the presentation now? Just very quickly. The way Coze addresses that specifically, we did do all this, see, we have the keys. Oh yeah, this is me saying we need you.
We want you.
Is we do canonicalization. And so immediately when we were looking at this, I was like, in JWT doesn't do canonicalization, and that's very typical in computer science. That's a very standard thing you do in computer science. I was like, why aren't they doing canonicalization? So when I mentioned that to people that complain about JSON and they understand that, usually we get them on board. Okay, you're doing canonicalization. So have you heard of normalization? Usually in terms of databases, you normalize data for a database. Has anyone heard normalization?
Sounds familiar, but I don't remember.
So normalization, say you have a record, and it's first name, last name, date of birth. But then the next record's date of birth, last name, middle name, first name. Then the next record's address, first name, date of birth.
Just making sure it's all the.
Yeah, so normalization would be okay, everyone has to have the same data, or we're going to sort it by first name, middle name, last name, date of birth, right? That's what normalization is. Canonicalization is normalization on steroids. So canonicalization is even more strict. So it's with it's not only sorting your data, but it's also specifying the particular structure of it. So that's how we do this. Is Coze transmits a canon with it, which tells you how to canonicalize the data. But this is technical details. It's not something that most people have to be aware of. But that's how we get around the JSON issues. And so I've gone rounds and rounds with some people about this. One of the complaints with JSON is JSON objects are not ordered. And that's one of the complaints we get. It's you can't hash over something that's not ordered. And our response is always UTF-8 is ordered. Right? You have to serialize JSON into a ordered format, and that's where we're doing the canonicalization is over UTF-8. And so some people complain about that. I think it's a silly complaint. It's a purist complaint that I don't think really impacts the design. But yeah, if you wanted, what was that?
A complain to complain kind of thing?
Yeah, I just don't think it's okay, well, what's the problem? We'll show them the method, be okay, here's the method, what's wrong with the method? They're like, well, just from a philosophical aspect, I don't like it. It's like, well, that's fine. You can have your philosophical complaint.
Changing colors.
Yeah, exactly, but it's still, we feel confident in design, and in application we found that it works really well. So like, JSON has problems. JSON definitely has problems. It's well understood this have problems, but people across the industry have tried to fix it over time. So, and we're using best practices with JSON.
Okay.
So, all right, any more questions? We're kind of late. We're almost at 4:30. So.
Okay, one last question.
Yeah.
Are you guys done working on Cozy, or are you still wanting to do more stuff with it?
There's all kinds of stuff.
Yeah.
Do.
Okay.
Yeah, there's
I
like
know
a
you
ton
said it was
more
open
stuff.
source. You still want to like add like so I
Yeah.
was just curious what you guys were trying to do more now.
Oh, well, and so one of the big problems JavaScript does not have a lot of these primitives implemented.
Okay.
So that's one of the big reasons why we haven't done more is we're just waiting for JavaScript to implement this stuff.
Okay.
And we're sitting around twiddling our thumbs, being like, okay, JavaScript, right? Like, when are you going to get this stuff?
And that
in?
one, Java is very like, it's not open or anything, is it? Is JavaScript open source?
Yeah, JavaScript's open source.
Oh, okay,
Yeah.
okay.
Yeah, so and it's implemented by the browser. So not only do you have to wait for JavaScript itself to like kind of adopt
Okay,
these,
yeah.
but then the browsers have to adopt them, and it can take a long time.
Okay.
This is another technical problem with JavaScript, but JavaScript is an interpreted language, and it does not run in constant time, and we need constant time guarantees for cryptography. So if you don't do things in constant time, I can do timing attacks against your code. So one of the problems with JavaScript is we're using some of the stuff that Coze has implemented in JavaScript. We're using a library by a Ukrainian called Paul Miller. And he's implemented some of these algorithms in JavaScript, but JavaScript itself hasn't implemented the algorithms. So we have a library that's implemented these, but JavaScript itself hasn't. So we don't quite feel totally confident releasing it.
Okay.
But Ethereum uses Paul Miller stuff for everything. So like there's like multi-billion-dollar corporations using his code for various things. So then we're like, well, everyone else is doing it. So, but we do have we're very conservative with implementing this stuff. But yeah, so more primitives is one of the things we want to do. We probably want to release a version 2 with just like, we probably need to change the name. There's a few other details that we want to change with Cozy, and we probably will do
Cozy
like a version
2.0.
Yeah, like a
There you
2.0.
go.
Just with some very minor adjustments.
Yeah.
A lot of people have asked us to do encryption. Even this week, I probably got like 2 people asking me to do encryption. So we're considering it.
That'd be cool.
So then Cozy would do hashing, signing, and encryption. Yeah.
That'd be so cool. See, that's something you guys could continue to work on.
Yeah.
Yeah. Okay.
So we're thinking about it.
Yeah.
But, so we have our thoughts. Go ahead.
I was just curious, like, how much longer is that gonna be too much for Cozy to run those 3 as well?
I think we can pull it off.
You
I
think?
think it's going to be simple enough to pull off. So there's another library. So Golang's crypto person, his name's Filippo. He used to work for Google, now he's not at Google, so he just kind of works when he wants on the crypto stuff. But Filippo released a library called Age. I think it pronounces it like Ahe or something like that, but I say Age. It's H-E. He wrote an encryption library. And so if Cozy does encryption, we're probably going to model it off of Age. I really like Age a lot. Age does not allow you to select primitives though. So if Cozy does it, we're going to allow you to select primitives. I would say that's one of the
Drawbacks.
drawbacks, but it's not as a big a deal with encryption as it is with signing to use different algorithms. Like the encryption algorithms we have are really, really good. Signing's more of an open question. Yeah, that's what we do. We just use Age. So Filippo's library is really good.
Do you have a lot of people from like ISA working on this too then?
No, we have like 0 people.
No, so who all like just people outside that you knew and everything like that?
Yeah, I mean, we've exactly.
That's crazy. That's cool. I was kind of in my head thought like this was like a project that you guys as ISA was working on, but no, this is just kind of like what you and other people were doing.
Yeah.
That's cool.
Yeah.
I kind of keep forgetting that all the people there have their own businesses, their
Yeah.
own lives and everything.
Yeah.
So I'm still just like just still in school, so I forget everyone has like other things going on sometimes. So, well, that's cool though.
Well, and as of right now, they're because they're professional organizations. They're not really working in technical stuff right now. So since this is like a technical thing, I'm not sure if this would be the proper like platform for that.
I get what you're saying. Okay.
But and right now in Colorado Springs, there's not much. I think there's a JavaScript user meetup, and I think that's it.
No way.
I don't think anyone else is meeting. Denver used to have a Go group, and I used to go to that group. I don't think they've met since the pandemic. So there's not a lot of professional technical groups meeting right now.
And like there's so much happening. Like there's more than there was before COVID and stuff. So it's gonna be like you guys meet. It's gonna be a whole catch up.
Yeah. Exactly. So, yeah, if you guys want, if you know anyone else that would be interested in hearing about Coze, I would love to present Coze.
Yeah.
Like, we want more people working on it, or at least knowing about it.
Maybe
or
we could
using
try
it.
to actually make a flyer to have people who are more interested in something like this to have more people come in. Like, not like people outside the club. You know how they like post like, oh, if you want to learn more about this, come to this room
Yeah.
where we host.
Because we can make this, if you want to present, well, it probably won't happen again this
You
semester.
could get paid
but
for
we can
it.
go.
Actually, yeah, we can like.
Oh,
figure- we
I'll
can
pay
actually
you
have
guest
him.
speaker. Yeah.
we can have you
So-
be a guest speaker.
Yeah, I think maybe in the spring semester we can probably make it a big event, like the CyberCons and all those AI events happening
Yeah.
here. We could probably do something on the flip side on spring's time, and then do something of that nature, so that way you could be a guest
Yeah,
speaker.
I would love to. However, I can do more evangelizing of this project.
Yeah,
would love
I
to.
would say
Oh, this is
if
very
not
interesting.
us, then Mark, Mark or Adam Bushes. I mean,
We
but
can
you already
have-
know them, so
Yeah.
just
We
be
can-
like, hey, you need a presenter? I got you. Like,
Okay. Yeah, I
Yeah.
should.
We can even.
But if
talk
not,
with them and
again,
stuff.
if not us, so. But
Alright.
if you want more, you said more people to work on. If students are interested in joining you, how would they best reach out to you? Just email or
The GitHub.
join your project?
Yeah, I think the GitHub is
The GitHub.
it's a good place. So you can do an issue or do so we have, let's see what issues are in. I don't even know right now. Oh yeah. So but yeah, this like does anyone use GitHub?
Yeah.
No, I've not.
No.
I've
Friends
only,
do
yeah,
that
only a little bit. I'm not
I
very
use other
familiar
people's
with it.
products. I don't.
So this is like in open source, by the way. If you like in Linux, someone knows open source, and I'm pretty sure Linux is on GitHub now. I'm pretty sure that's how they manage the project. But you know, GitHub's the Facebook for code. So yeah, like
Yeah.
on here, even do a pull request, just like hello, right? Hello world, and it would be like, oh hi, it's good to meet you. But yeah,
What?
GitHub's a great place to manage the organization of that. So,
Okay, cool.
but yeah, if anyone else has any questions, as I said, we've been doing this for, so it did take about a year of development. I would say probably 1 year of full
Okay.
development to go from zero to a pretty complete product with it. But
Okay.
we can talk on and on and on about, so we just kind of scratched the surface of some of
Yeah.
this stuff. But that's a good introduction.
That is so cool.
So who's, I guess, in a perfect world, what like company or group do you want this to go towards?
So I think I would like to see every single social media platform adopt it.
Okay.
So
Yeah.
they could immediately, social media platforms, they could load a key in your browser, or however they want to manage the key. The key management is a difficult thing, but they can figure out how to manage the key, but then they can sign posts. So you get two things from it. You get, I can make sure that user's the one that actually said that, which is a huge deal. Right now, we're just trusting these platforms. But two, it secures that message forever from tampering.
That's so cool.
So then they can't change the database. If someone changes the database, we know something went wrong. Or if someone's archiving it, I still know you said it. Or if a third party takes your post and archives it someplace else, I still know that you're the one that said it. And you said it at that time with that information.
Right.
So yeah, I would love to see it go applied across the board. I think this is a layer that's easy. Oh, one of the things I did not talk about, actually, let's go back here. One huge use case, I should have talked about this. It's password replacement. You don't need passwords, right? So you can use Coze to log in. So I'm just going to hit login, bam, I'm logged in. So I use the key in my browser to sign a message to say, this is Zach, and it just logged me in. So that's an example of what you can do. So actually,
Could you use that for other things, not just here?
yeah,
Oh,
I can use it for a zillion different things. So like, this is an example of all of these are Coze messages that are signed, right? So when I'm creating products, so this is an example of me like creating a product, and it is, I don't know why I keep on doing that, but everything's cryptographically verified.
Mm-hmm.
But yeah, this would be example of like all these ACs. But logins, updates, anything that you do on, so the way this website's created is anything you do can be verified by a third party. So if you do anything on the website, you do a message, you sign something, you edit something, you log in, all of that can be verified by a third party. So it's kind of, we're trying to get to like the big vision behind this ultimately is to get away from actually social media platforms. So like you can say something and then everyone can adjust it, right? And we don't care which platform it's on, right? So if we can get to that point, so what you're missing is that authentication layer. So if you can get an objective, agnostic authentication layer on the internet, you don't have to worry about which walled garden is going to. It just exists. It's just there.
Oh, wow.
So ultimately, that's what we would like to do. So, and we're, by the way, we're working on that very diligently right now.
Mm-hmm.
So
That's so cool. How many would you say right now is working on this project with you?
just me right now. I have had other people work on this
Oh, okay.
for the moment. Like right now, this is kind of like back burner, not like full time
Yeah.
on it, but hopefully in the next couple weeks, doing another like push
Oh, wow.
on this sort of
This
stuff.
is that's a lot to do on your own.
Like there's parts I'm doing and then there's parts other people are doing.
Okay, I see. But
So
like for this section you're doing, you're
Yeah.
all doing alone.
yes,
Okay.
yeah, for right now. But I have had so this website had a software engineer I contracted with for about 3 years.
Oh, wow.
Doing it. So
Cool.
and some other people. We've had open source contributors. We've had other.
Awesome.
We've had Austin Tapia from the university was helping us with
Do you
some
ever
stuff
like have people help you and you never even actually meet them? Then
all the time.
all the time.
I have
Okay.
all kinds of friends like that.
I have friends, but I never see them.
Yeah, I've never even met them.
You only talk to them, yeah.
It's just the
virtually.
friends you've never
Yeah.
met. Yeah. No,
Well,
that's so cool.
Yeah, I mean, some of these guys, like, one of them I met, like, on, like, cryptocurrency forums, and I met them someplace else, and then finally I met them in another forum, and it was, like, a forum of 100 people.
Oh my
And
gosh.
it's just like, okay, it's a small world.
Yeah.
It's not that big a world.
I guess you're right. You know, there's not a lot of people who really do like the technical stuff that you talk about. See, this is just a whole tip in the iceberg you're just talking about and everything. I was like, what?
You realize how little you actually know.
Yeah, I know. I was like,
I feel like I thought I knew. I know. Okay. So
like I'm shocked that you had like I remember you said you could give like a whole presentation alone on like just the information theory. Like
Yeah. Well, yeah. So,
Yeah,
and
that's
that's
crazy.
Yeah, and I do a lot of work in, like, information theory, too, so.
Yeah.
I just finished.
Is it kind of like a philosophy thing, more in a way?
It's basically Shannon started information theory.
Okay.
So it's like all Shannon's work, but I don't know. A lot of the questions I had in mathematics were answered by information theory. So things I didn't understand in class in school, like
Yeah.
information theory is like, oh, okay, I finally
That's so cool.
like why is this stuff secure? Information theory is the answer. So Shannon's his paper was 1949. He wasn't trying to do like information theory. He's trying to send like phone calls, right, for Bell. He's trying to make phone calls and he's trying to figure out how much information they can put on the wire. The way he proved information theory was fundamental was using encryption, which is mind-blowing. He's using encryption and using base conversion. So converting from one base to another is how he proved it. Mind-blowing, like that someone had that insight. So, but yeah, information theory is just telling me how much information is in something, right? Like, so if I want to be able to measure how much information is in something, information theory is going to tell me that.
Yeah.
So,
That's cool.
yeah, I'm doing a lot of historic study right now on Shannon
Yeah.
and Turing. So
That's so cool.
Yeah.
Do you have an image in one of those?
I do, yeah.
Okay.
Yeah, so there's all kinds of stuff you can do. I want to find a better
Because
one.
that's kind of what I was wondering, like if you could do like audio, if you could do images, but
Yeah,
it looks
absolutely.
like you could do everything, which is actually pretty amazing.
I don't want to have like too crazy images in here. Okay, so like this is this was someone that was using our product.
Yeah.
So that image, so the way that we get Coze to sign this, right? Because this isn't like text. Like how does Coze sign a digital file? Well, we hash it, right? We hash it and then we get 256 bits and then Coze signing that. Right?
Okay.
So, but it's anything, right? Anything, we can sign anything, right? Like literally anything. So we could take that chair, if we can serialize that chair, right? And then we can hash over that, the atoms in the chair, right? We can do it. But, and like, I always like bringing up like the crazy stuff you can sign. So this would be an example of one of the things that we're we're solving is like, I ordered this from Amazon, I ordered this from Walmart, same company, right? This one's a knockoff, right? And I wouldn't have known that as a consumer. Right? How do I know that this was
Yeah.
fake?
Wait, how did you know? Yeah.
Well, because I had already prior ordered from this.
And it would just look, it was different. And so you're like, that is not real.
But yeah, Walmart, so this was from Walmart. Walmart shipped me a knockoff, right? It happens all the time. So it happens with supplements like constantly, which is really dangerous. But yeah, so this is like one of the things that we're doing. I'm trying to find. Oh, we have items. What else can I show you? This is like website stuff I'm showing you now. But filter print test? I don't even know what that is. Oh, okay, yeah. We were doing stress testing on this. I was like, what is that? But like, yeah, so that's just a home, like all of these are signed, right? So we were doing a daylight test on the stickers to see how well they survive. But yeah. So everything's signed on here now.
What? That's so cool.
You have those URL stickers, right? You were talking about the chairs or tables in Fuel and Iron that you're like, all these are ours.
Yeah.
All these, those are the same ones, right?
Yeah, they're the same stickers. Yeah, so Fuel and Iron, if you look under the tables, they have all of our stickers on it.
That's so cool.
Yeah.
So you just scan and be like, oh, this is ours. I signed this.
Well, yeah, yeah. So it's just for fun.
Yeah, that's so cool though.
Yeah,
And if you ever lose those stickers, you can always reprint them again. Like you don't have to worry about regenerating.
exactly. Yeah, yeah. So we have a few applications of it, but we're all over the place right now. So
Gotcha.
so anyways.
No, that was amazing. I'm so shocked.
Yeah.
That's a lot.
I think you'll
Clap everybody.
Okay, yeah, and here's my water bottle, right? Like, so there you go.
Oh, that's so
So if
cool.
you scan it, that's what you get. You just get the water bottle. But I should log. I don't have anything on my laptop. I could actually show you some of our customers' profiles where they're putting this on our profile. The problem we found, by the way, I know we're totally talking about something else. The problem we found with this is actually just the application of this onto products is a huge deal. It's a really problem for these consumers. So Amazon, the way they're getting people to do it is they're giving them a discount to apply it. And so people are like, oh yeah, we want to save money. So they're doing it. We can't get people to put these codes on their products, even if it's saving them money. Because they're saving money from the counterfeits, right?
So it's like them actually putting it onto their
it's
thing.
very difficult. Yeah, it's very, very hard. So that's the
Why
hardest
not
problem.
though? Like, just do it. At least if someone accidentally lost your water bottle, someone saw it, and you're like, oh, I know who it is. No.
Yeah.
Well,
So
how much does it cost for it then? If I want to do the same thing as you, put it on my water bottle, so then that way I know this is my water bottle.
Yeah.
I mean, for you, like absolutely, like if you provide the materials, right, like free.
Oh,
So
all right.
This is just this is like Avery labels. You can use Avery labels. You can use whatever you want.
So it's just like actually printing it onto like a thing.
It's the application onto the box.
Okay.
Is that's the thing that we did not expect to be very difficult. So companies hate doing it. They're not well designed logistically, and then a lot of them are using like third parties to fulfill for them.
Okay.
So they're like, our third party is not going to do that for us.
Yeah.
It's like, oh, okay. Well, all right. So yeah, that's how Amazon's applying it at the warehouse too. Amazon's saying, hey, if you ship it to us, we're going to verify from the carrier that came from you, and then we're applying the stickers because it's too hard for you to apply the stickers. So next time you get something from Amazon, look at the transparency stickers. So, anyways, like that's another out there. If someone wants to work on that problem, we are ready. Like we're working on some other things right now, some other clients, but like we just need someone to work on that. Like, and we'd be so excited.
Just like the market and everything.
Yeah, like working with customers, solving that problem. Like probably getting a list of vendors that have applicators that work for various situations, and then when the business says, oh, how do we do this? We're like this, and this, and this.
Oh, social
Right,
work.
these are these
I got
options.
you.
Right? Yeah.
That's
like,
so much easier.
we need that. Well, yeah, we need the social part, absolutely.
All right.
Yeah. So like not highly technical, like just someone that's friendly and works well with businesses. So
I can do that.
so
He's like, that's my new job now.
Well, it's like this whole presentation. I'm like, I don't know if I
But
can
now
do
you're-
that. And then I found something like, I can do. Talk to people. I can do that. That's easier.
yeah. So earlier in my career with State of Colorado, I mean that's what I was doing. Right? The State of Colorado was like, well, we don't know how to do this. I'm like, okay, I got you.
Yeah.
Like I'll figure it out. So But yeah, so that's a big thing. It's like some sort of applicator, a known price, and printing. So they know how to do it. The rest of it's built out. The rest of it's like good to go. It's that last part of getting the consumers. And we have another part that spent a lot of time on this. We have a patent on this. We spent a lot of time on this because we need to make sure that it's very scannable. Because consumers will not scan it if it's hard to scan.
Yeah.
So even transparency, when I try to scan the transparency stuff, can't scan it. Like Amazon, well, what good is this, right? What good is it if no one can scan it? So we have a patent on that. It's very particular how it works, but I think it's good. So it's just finding the vendors that can do it. Most of the supply chain is designed for stickers that do not change. So these stickers have to change on every product, and that's the other problem. Is that the supply chain is just not designed for that. So like vinyl stickers with a unique QR code on it, the supply chain is not good with that. So typically they're doing like LaserJet. They have to print unique information like Best Buy date. They're doing a LaserJet while it goes through. Is how they're doing it. So that's a whole other problem. It's just finding the vendors that work well with this. It's good quality. It's not going to smear. The consumers can scan. That's a hard problem and affordable, right?
Yeah.
People aren't going to be spending $1 on a sticker if they're applying it, but even a few cents is too much for a lot of these businesses. It needs to be very, very cheap for these businesses to use it. But then you have savings that Amazon's not selling counterfeits on your behalf, right? So with like Snap Power, right? That would have been a sell for Snap Power. Instead, that went to the counterfeiter, right? So immediately they're making money. So, anyways.
Yeah.
This whole different thing. That's the application, right? So that's the application of Coze. So now
That's so cool. There's a
better
lot to it
application.
though. I didn't realize you could
All right. Well, it's almost
do so
time.
much.
Yeah.
Yeah.
Okay, cool. Thank you very much.
Thank
Yeah, thank you.
Thanks for coming.
That was amazing.
Yeah, thanks for having me.
We'll clap.
Yeah,
Oh,
I know.